Okay, word up. Regression. Here's some points. I made these up. Here's a plot of them. I made that too. I want to find a line that goes through these points well. So we'll actually find the best line in just a second. But to begin with, we want to consider that. All right, let's take for example these two lines, 1x minus 8 and 1.1x minus 0.05, and consider them in this situation. So I have to choose between these two, which is a better fit. Both of them go through 2 points. It looks like blue is lower, so it may not be as good, but I need some kind of solid criteria for doing so. So what I'm going to do is I'm going to decide, well, which of them are, on average, the closest to these actual data points. It looks again like blue is closest to 2 out of the 6 and green is closer to 4 out of the 6, but we want a real measure for that. So to do so, I need to know what the value of these lines are at each of these points. When x is each of these values, 2.1, 2.8, 3.4, and so on, I need to know what these equations give me for y, and then I'm going to take the distance between those values in these points, and I want to minimize that distance. So here are my y values. Again, I'm just looping through each value in a and plugging it into this function that I created here. And I get these values. Okay, well, let's see. What do those look like? Again, those are the values that are actually on the line. So here, these five red dots are those y coordinates that are actually on that line. These 5 green dots, the y coordinates that are actually on line B. And I'm going to find how far apart are they from the actual data points. See, some of them are pretty close, as we can see. Okay, reminder about our list notation. Remember, a of 0, this means the first element in that list A. That's the first x coordinate, first y coordinate. Right, first y coordinate on line A, first y coordinate on line B. So what I'm going to do is I'm going to take the difference of the actual y coordinate, which is our list B, and those predictions, and square them. And that's what I'm going to call the residual. So I'll get the residuals for both of those. Okay, this is how far away that first point is from line A. This is how far apart this first point is from line B. You see it's much closer. The second point is incredibly close to line A, whereas the second point is not that close to line B, and so on and so on. So I have each of these individual values, but now I want to combine these. I'm going to combine these using root mean square error, which means that I'm going to add them up and take the square root of them. So in my formula, that's why I'm just taking the square root of the difference between these values squared, aka the absolute value. And my root mean square error for line A is 1.83, for line B 1.37. So this guy is much closer, or not much closer, but it's closer to the rest of those points than is line A. And that's exactly what we thought was going to happen. This upper line, this line B, is closer to the actual data points than is line A on average, even though there's a couple of points that line A is closer to. Overall, line B is closer to these data points. And we can just hop in here. You know, there's that first point. It's right up on that line. The second one is right here, and so on. Okay. Again, that was about deciding which of them were a better fit. But we can also just actually find the fit very easily with NumPy. So we're going to fit a polynomial to our two data sets, the x, the a, and y is b. And this 1 stands for that it's a straight line. It's a linear function that I'm fitting. This function NP polyfit will give me the slope and y-intercept of the line that best fits it. So then I can just go ahead and say, okay, well now I have this line of best fit. And I assign slope and intercept to these variables that spit out from NP polyfit. And I can plot those. And if I look at my graph now, there is my line of best fit. This actual line of best fit is sneaking through both of those. Okay, and if I were to look at the root mean square error, it would be less than what I found for each of those. That's why it's the line of best fit. Okay, but this is the syntax for finding a straight line of best fit, the slope and intercept for the straight line of best fit. Then I have to define a function. Then I plot that function. All right. So another example, maybe I have this problem where I have some data from Mendeleev about the temperature and solubility of sodium nitrate in water. I'm going to create two lists, temperature, solubility, and I'm going to answer this question. Based on the scatter plot and the value of the correlation coefficient, is it reasonable to use a linear function to model this relationship? Well, let's take a look at it. Sure looks like a straight line, so I think that that's going to be reasonable to use. Well, let's use it. Again, I'm going to use NP polyfit 1, and I'll just print out what the slope and the intercept are. So slope is 0.87, intercept 67.5. Now what I can do is go ahead and plot that line of best fit. Again, it's just the slope times x plus the intercept that I've assigned up here. That looks like a pretty good fit. Looks like a pretty good fit to the line. So besides for using NumPy, there's another really great library called SciPy. And SciPy has a linear regression fit as well. That gives me a little bit more information. And in fact, instead of just the slope and the intercept, it also gives me a correlation coefficient, p-value, and the standard error computation. So this is, I have to first import from SciPy the stats library. And then I want to use the statslin regress tool, and I just pass the temperature and solubility in before. But now, instead of just slope and intercept, I have these added three values, the correlation, the p-value, and the standard error. If I print these guys out, I end up with something similar. Now, the correlation coefficient, I want this to be close to 1. And because it's 0.9989, that tells me that this is explaining quite a bit of this data. This line is able to explain almost all of this data. We'll talk more about the correlation coefficient, but for now, what's important is that you're able to instantiate the model and evaluate it. Okay, given some data, find the line of best fit. So last, here I made some random variables. Or I'm going to make, I didn't mean to have this there. I'm going to make some random variables, x and y. And again, I'm going to run this statslin regress on those. So this is just going to be a bunch of random variables. This is going to be a bunch of random variables. If you set this, you should end up with the same thing that I get here, which is the slope, intercept, and r values of 0.12, 0.55, and negative 0.11. Negative 0.12. And I can take a look at this. Okay, well, if you look at the correlation coefficient, it's 0.11 here. That is not very strong. That is not able to explain a lot of this data. And sure enough, if we look at the picture, we should see that. This line is not very close to a lot of the data. And that's what the correlation coefficient tells us. Because it's not close to 1, it's not able to explain a lot of the data. This is where our understanding should be to this point. You should be able to generate a plot, find the line of best fit using either NP polyfit or stats-lin-regress. I would recommend stats-lin-regress. And it would be nice if you were able to include that information in a plot like I've done here by adding text strings. You can just copy and paste this and change whatever you'd like to change about it. Yeah, so linear regression.